again starts at the same point, but rather than fanning out at a constant rate, they actually fan out at an increasing rate from one another. Okay.
What kind of grids have concave demand?
What?
What kind of grids have concave demand?
A good where it sort of has the same value for everybody. Right? Yeah, I mean, so like, for example, imagine that people had a distribution of willingness to pay, which was like a unimodal thing like the normal distribution. Then it's going to be concave up to the point where you reach the one mode, and then convex beyond that.
Okay.
Right? Actually, one of the problems on your problem set talks a little bit, on this tough problem set you have coming up, talks about that a little bit. Okay, so another way to write marginal revenue is price times 1 minus 1 over the elasticity of demand. And Eric, could you derive why that's the case? You do it on the board or?
Okay. Well, actually,
It's P prime times Q, right? Was the marginal revenue is P plus P prime times Q. How do we turn that into P plus 1 minus 1 over the elasticity of demand?
So obviously the P times the 1 is the P. So
Yeah.
somehow we're supposed to get negative 1 over elasticity equals, should equal P prime Q over P, which,
Yeah. That's the elasticity.
oh right, but that's it, right? Because P prime is del P del Q.
So you just do 1 over that. Yeah,
Right.
exactly. Exactly. So the elasticity is negative dq dp divided by P over Q. And so negative 1 over the elasticity is dp dq over Q times Q over P. And therefore P prime times Q is just negative P over the elasticity, which is the difference between the marginal revenue and the price. Okay. So one thing this immediately tells us is that whenever the elasticity is less than 1, marginal revenue is negative. So the elasticity of demand determines the level of prices, right? And you're never going to want to produce at a point where the elasticity is less than 1, because then your marginal revenue will be negative, and assuming you have positive marginal costs, you'll never do that. So elasticity of demand summarizes, in some sense, how big you are in the market, how much substitution there is to outside goods. We rearrange this formula, we get that the markup that you charge, P minus MC, relative to your price is equal to the inverse of your elasticity. This is the learner's pricing law.
So suppose the elasticity of demand is constant.
Yeah.
Then that is less than 1. Then in
Yep.
that case, monopolists, there's no chance for monopolists to make sort of additional profit.
No, so a monopolist in that case can actually earn infinite profits.
Okay.
Because he wants to constantly be reducing his quantity, but it turns out that if you take the limit as Q times that price goes to 0, it approaches infinity. Because that demand curve is a messed up demand curve, right?
Yeah.
Because it has infinite surplus underneath it, right? If you integrate the surplus underneath that, it doesn't converge, right?
Okay.
So that's the basic problem. If credit cards, okay, so this can be problematic when the price is negative, because then the denominator here is negative, right? And so, for example, think about a credit card, right? A credit card basically gives you points. That's basically a subsidy on you, so it's basically a negative price. Therefore, this measure is not going to be very useful because the left-hand side is going to be negative. And so in that case, it often makes sense to just use the marginal surplus as the measure of market power rather than the inverse elasticity. But sometimes you see both showing up. Okay, so this is sort of a simple story, but you can apply it even when there's some additional wrinkles. So first of all, imagine that demand is not known. So we've assumed a simple price-quantity relationship. When demand is uncertain, you don't have a simple price-quantity relationship. So imagine you don't know how many people are going to be willing to buy your product at the price that you've charged. Then you have to produce some, but you might end up having a surplus, or you might end up having a deficit, right? Turns out you can still use a version of the Lerner rule, but rather than using the elasticity of just the demand function, you have to use the elasticity of the average quantity that you'll end up selling with respect to price. And your marginal cost will be the marginal cost of the average additional unit you sell, rather than the average unit that you produce. Okay, and there's a paper by Mike Salinger about that. Another version of this is that you might try to learn about demand, right? And a natural way to do that is to try varying your prices and see what the elasticity of demand is, basically, and then use that to set your prices, right? So doing that based on past experience is a very good way to go. But Ilya Segal in a 2003 paper came up with something even more clever than that, which is that you can learn based on the people that are currently entering. So what you can do is you can say to everyone, report to me how much you value the good. I will give it to you if it exceeds the monopoly price. What is the monopoly price? It's the optimal price determined by the distribution of everybody else's reported valuations. So I use everybody else's valuations, I fit a curve to that, and then I set a monopoly price to you based on that. But you should report to me your valuation truthfully, because that's going to be what determines whether you get to buy the good or not at the monopoly price that I set for you. And it's just a take it or leave it offer, so you want to report truthfully. Right? So that's kind of a clever thing. That's rather than putting people in any particular sequence, you can sort of like test around the demand all at the same time. Okay. One place where not this incredibly fancy version that Segal did, but the more intuitive, we test out different prices and we see what happens, is really easy to do, is on the internet. So Laurent Aynave and co-authors collected data from experiments on eBay. And what they did is they looked for cases when a particular seller was selling a good at many different times or even simultaneously at different prices or different other characteristics in different auctions, right? And they interpreted as times when sellers were experimenting to try to figure out how they should set the terms of their sales, and rather than having to run experiments themselves, they could use the experiments that everybody else had done. They used this to construct a demand curve for an auction. So what does a demand curve in an auction mean? Does anyone want to try to explain? Anyone look at the article?
It's a probability of buying an object
Yeah.
within a certain time by setting the different initial price.
That's close. That's very close. But there's the question is, what is the price that you're setting? Because it's an auction, right? The price is being determined by the auction. So what's the price that you're setting?
You mean usually there is some, I think, minimum price.
There's a minimum price, but that's not the price you can end up selling the thing at. So that's not really a demand curve. So the question is, if you raise that reserve price,
Right.
on average, that's going to raise the price you sell the good at. Why? Was there some chance that there's no second highest bid? Or that the second highest bid is below the reserve price, in which case it's raised the price you're paying. But in exchange for that, it also reduces the probability you make a sale. And if you trace out the locus of that relationship as you move around your reserve price, that gives you sort of a demand curve. Okay. What they found was that if you look at lots of different categories of products of lots of different values, you get very different demand curves because the products are worth different amount, but the basic shape of the demand curve is very similar. So they took different categories of products that have different sort of list values, they divided by the list value, and they found that across all of these, the demand curve looks roughly like this. Here are the different curves, they look like this. I fit a third degree polynomial to those, and I got this. I then used that to derive a marginal revenue curve, and the interesting thing is it has this non-monotonic shape. What does that mean? Well, if your value of the object, which is your marginal cost of making a sale, is here, there are multiple intersections with the marginal revenue curve, right? And your marginal cost of making a sale is just constant, right? Because if you make a sale, you get to pay that cost. If you don't make a sale, it doesn't matter what the probability of you making that sale is, right? So you'd have some constant marginal cost, and you're going to find its intersection with your marginal revenue curve, but now here you've got multiple intersections. So what do? Well, imagine that it intersected down here. What would you do? Would you sell with probability, 0.9 and therefore charge this price? Or would you sell with probability, 0.3 and therefore charge this price up here? What do you guys think?
0.99.
You sell with 0.9. Why?
The expected gain is higher.
Well, because the area underneath the marginal cost and above the demand curve is smaller than the area underneath the marginal revenue curve and above the cost curve, right? So on net, you would get more from going here. But on the other hand, imagine that your costs were up here. Which would you do? Would you charge over here, or would you charge over here? Over to the left, right?
Cheaper price, yeah.
Right? Because the area underneath the cost and above the marginal revenue is bigger than the area underneath the marginal revenue and above the cost. Okay, so that gives us a really intuitive and simple way to try to get rid of this complexity that comes from multiple intersections. We can draw a line that's exactly at the point where the area underneath the marginal revenue and above the marginal revenue, between this line and the marginal revenue on each side is equal, right? When you draw that line that's called the ironing line, then that can just replace your marginal revenue curve. You can just get rid of this part below and this part above, and you can just treat it as if your marginal revenue curve looked like this, because you're never going to produce in these parts that are cut off.
It is different from the principle regarding the stability of the equilibrium. You mentioned earlier, like demand curve is, I think, more negatively sloped than supply curve.
Yeah, that's a good question. So that's a question I've had for a while. So this is for an optimization problem.
Right.
But you could ask for an equilibrium problem. Are there like areas that you could sort of cut off of the demand curve because you'll never see them in equilibrium because those will be unstable? I don't think anyone's tried to develop the theory around that. I also don't think anyone's tried to develop the theory of this in multiple dimensions. Because in multiple dimensions, imagine we had a two-dimensional thing for like two products. You wouldn't just iron below and above, you would like iron out areas that were sort of non-concave in some sense. You know what I mean? But I haven't seen anyone try to do that. I think it's an interesting topic. Okay, so, however, this just summarizes what I was just saying. So the ironing line is the line where you have equal area above below, and then what you find is that as cost moves from just below the ironing line to just above it, the quantity drops discontinuously, and the price jumps discontinuously from here to up here.